All right, so far we were discussing Gram-Schmidt orthogonalization in our last video lecture. So we will continue that discussion, and in this lecture we will try to solve some problems on Gram-Schmidt orthogonalization to strengthen the concepts. So let's have a quick recap of the Gram-Schmidt orthogonalization itself. So if you are given a set of signals S1, S2, S3 up to Sn, which is a general scenario, then you can find out the orthonormal basis functions that represent the signals in a same signal space. So you start with phi 1, which is basically the first signal S1 divided by its norm, and then you move forward, you define phi 2 dash, which is S2 divided by its norm minus the projection of the same on phi 1 axis, and then you normalize phi 2 dash to get phi 2, and then you proceed in a similar manner in an iterative fashion to get phi 3 dash, which is S3 divided by its norm minus the projection of the same on the phi 1 and phi 2 axis, and then you normalize phi 3 dash to get phi 3, and so on until you get a general expression which is phi k dash, that is equal to sk divided by its norm minus the projection of the same on all the other phi j's from 1 to k minus 1, and then you can normalize phi k dash to get phi k, and then the projection is defined by this particular expression here, and that was the general Gram-Schmidt orthogonalization process. So now let's try to understand it better by applying that to some real problems. So let's say we have a signal, or rather a set of two signals, S1t and S2t. So this is an example of, let's say, a binary communication system. So let's say whenever you have a 0 transmitted, you are mapping that on signal S1t, and whenever you have a 1 transmitted, you are mapping that to S2t, and your S1t and S2t are given here. Okay, so this is your S1t, which is a signal that is having an amplitude V between 0 to TB, the duration of the bit, and then you have S2t, which is a signal that has an amplitude minus V between 0 to TB. Okay, so you have to find out the basis functions for this. So the usual way of doing this is, let's say the first step is your phi 1. If you recall from Gram-Schmidt process, this is basically your S1 divided by the norm of S1. So what is the norm of S1? To calculate norm of S1, you have to find out the energy of S1. So basically norm of S1 square is basically the energy of this signal S1. So S1 square t dt, if you integrate it from 0 to TB, then you get the norm square. Okay, so this thing, what is this integral? S1, you can see, is defined as V between 0 to TB. So between the range of interest 0 to TB, my S1 is basically V, and square of S1, so V square, and then we have dt. So now this basically computes to V square TB if you compute this integral. So basically the norm of S1 will be the square root of this number. So here your phi 1 is basically S1. So this is, if I don't write the t in parentheses, it is implied that this is a function of t, and we are visualizing that as a vector. So S1 t divided by the norm of S1, which is the square root of this this term. So basically this will be v root tb. So this is your phi 1. Now what will be your phi 2 then? So let's try to compute phi 2. So phi 2 prime, so that will be your S2 divided by the norm of S2 minus the projection term. Okay, so the projection term is basically the projection of S2 divided by the norm of S2 on phi 1. So you have to multiply it with phi 1 and this times dt, and then the whole thing multiplied with phi 1. Okay, and this integral of course has to be between 0 to tb. So you see S2 also has energy if you calculate, since if you're squaring S2t, so minus v is also becoming v square. So between 0 to tb your S2 square is also v square. So this integral for the norm expression will give the same expression v square tb as you got in case of S1. So basically this phi 2 dash will be S2 divided by v root tb, because the norm of S2 is same as that of S1, which is v square tb. And then if you compute this expression, this will give you so if you plug in all the values, let's say your phi 1 is basically S1 divided by v root tb. So basically here you are getting 0 to tb integral. Your S2 is minus v between 0 to tb, and your phi 1 is S1t divided by v root tb. So let's say this is S1t, then divided by, so your norm of S2 is v root tb, and then the phi 1 also has a denominator v root tb. So basically there will be v root tb square in the denominator. And then if you calculate this, so you see here you have minus v, your S1t is plus v between 0 to tb. So this particular expression will be just this part. This part will be equal to integral of 0 to tb. I'm putting the value of S1 between 0 to tb, which is v. So the numerator will be minus v times plus v, which is minus v square, and then in the denominator you have v square tb, and then you have dt. Okay, so this will be so this v square and v square cancels out, and then this will be minus 1 over tb, and okay, this is the whole thing is also multiplied by phi 1 here. So this will be this will be minus 1. Okay, so basically this will be the integral will be minus 1 because you have a TB in the denominator and then you have TB in the numerator if you work out this integral. So this will be minus 1. So eventually if you write it freshly, the expression for phi 2 dash will be S2 divided by the norm of S2 minus minus of phi 1. So this minus sign remains, this integral is 1 and then here is a phi 1. So basically this will be plus of phi 1. Okay, so so now your phi 1 is S1. Okay, so phi 1 is S1. Let me write it out. So this is S2 divided by V root TB, which is the norm of S2, plus S1 by V root TB, which is your phi 1. So your phi 2 dash is basically, if I write it again, your phi 2 dash is S2 plus S1 divided by V root TB. Okay, so S2 plus S1, what is S2 plus S1? Your S1 is plus V between 0 to TB and your S2 is minus V between 0 to TB. So if you do S2 plus S1, then this will be 0. So basically your phi 2 is also 0, which is the normalized version of phi 2 dash according to Gram-Schmidt orthogonalization algorithm. Okay, so if you do this math properly, then you can see that what I have is very interesting. So what I have is basically your let me write it fresh. So your phi 1 as S1 divided by the norm of S1, which in other words is S1 divided by V root TB, and your phi 2 is 0. So you need only one basis function to represent these two signals, S1 and S2, and your phi 1 is basically S1 divided by V root TB. So if you look into S1, your phi 1 will look the same, but the amplitude will be changed. So the amplitude, if you are dividing S1 by V root TB, so basically this is the amplitude will be V divided by V root TB throughout the range of this signal. So basically it is 1 over square root of TB, the amplitude. So your phi 1 looks the same as your S1, and that's what you all need. You don't need phi 2. And if you represent the signal, so now if you write the signal, so let's say your S1 is basically V root TB times phi 1 plus, so you don't have another dimension, so you can maybe write 0 times phi 2 just for your convenience. So it's still a two-dimensional signal space, but we don't need the second dimension to draw the signals. Okay, and your S2 is basically as you can see is minus V root TB of phi 1 plus 0 times phi 2. So your S2 is nothing but minus V between this these intervals. So you can write S2 by looking into these figures as minus of S1, and S1 is phi 1 times V root TB. So you can write S2 as minus of V root TB times phi 1 plus 0 times phi 2. So now you can see you can still have a two-dimensional signal space. So like this, I'm sorry. So you can still have let me erase this. So you can still have a two-dimensional signal space, and like this. So this is your phi 2 direction, but your two signals S1 and S2 are not required to represent in terms of phi 2. So basically, if you imagine this as an xy coordinate plane, so both these signals are along the x-axis. So this is your S1, and the amplitude of S1 is V root TB, so which you can also write as square root of E, where E is the energy of the signal. Okay. So you can write as square root of E as the amplitude of S1. This is same as square root of V square TB or V root TB, and for S2 you have the same amplitude but in the negative direction, so minus of square root of E. So you can which is same as minus of V root TB. So you can represent these two signals on the two-dimensional signal space, but you don't need the phi 2 really. So you can have all the signals along the phi 1 direction. So this is how you can work out, given a set of signals, you can work out using Gram-Schmidt procedure and find out the values of your phi 1, phi 2, or if you need more basis functions like phi 3, phi 4, etc. And as you see, the stopping criteria is wherever you get a phi I equals to 0. In this particular case, your phi 2 is 0. So you stop at phi 1, and you can represent both these signals in these examples in terms of phi 1. Okay. So if you work out similar examples, you can see the same rule applies everywhere. So let's say you have your S1 as this and your S2 as this. So I want to calculate phi 1 and phi 2. Okay, so the answers are given here, but let's work this out. Let's work out one more example. So I will move to this whiteboard here. So let's say your phi 1, sorry, your S1 looks like this. So let me redraw your S1. Okay, so let's say okay, something is wrong. Let me use another board here. So let's use this one. So let's say your S1 looks like this, right? Let me see. Between 0 to TB, so this is your 0, this is your TB, and this is your V, and this is your minus V. Okay, so this is your S1. Okay, and your S2 your S2 looks like continuous amplitude between 0 to TB. So your S2 is V between 0 to TB. So now let's work this out. So the first step is to find phi 1, which is S1 divided by the norm of S1. So the norm of S1 is norm of S1 square is S1 square between 0 to TB. Okay. So if you look into your S1, it's basically plus V between 0 to TB by 2 and then minus V between TB by 2 to TB. So this is halfway between 0 to TB. So you can split this integral between 0 to TB by 2, and in that interval S1 square is V square dt, and then the next interval is TB by 2 to TB, and in that interval your S1 square is minus of V square, which is equal to V square. So this is basically V square TB by 2 plus again V square TB by 2, which is equal to V square TB. Okay. So S1 norm of S1 square is V square TB. So norm of S1 is square root of that. So you obtain your phi 1 again as S1 divided by V root TB. Now what will be your phi 2 dash? So phi 2 dash is S2 divided by the norm of S2 minus the projection part. So I can write it like this. So the projection of your phi 1 on S2 divided by the norm of S2. Note that I am omitting the T within the parenthesis, but you may or may not have it, but the main point is that you have to appreciate that they are same. So the time domain functions are represented as vectors. So this, and then the whole thing multiplied by phi 1. Okay. So S2, the norm of S2, you can see from this figure, the energy of S2 is V square TB again. Okay, because you are squaring S2 within this interval, so that will be V square, and then the integral will work out as V square TB. Okay, so this will be S2 divided by V root TB minus, okay, minus, so your phi 1 is, so let me put the values here. So integral 0 to TB, phi 1 is S1, so S1 times S2 divided by norm of S1 times the norm of S2. So S1 times S2 is basically V square between 0 to TB by 2 and minus of V square between TB by 2 to TB. Okay, so if you split this part remains the same, minus if you split this between 0 to TB by 2 and TB by 2 to sorry, I missed this phi 1 here. So if you split this integral between 0 to TB by 2 and TB by 2 to TB, then you can write so this part on the numerator between 0 to TB by 2, it is V square S1 S2, and the norm of S1 is square root of v square TB or v root TB, and for S2 also it's the same. So if you are multiplying the two norms together, then in the denominator you will get v square TB. Okay, so this multiplied by phi 1 minus TB by 2 to TB. So between TB by 2 to TB, this S1 S2 is minus v square, and then you have v square TB in the denominator, and then the whole thing multiplied by phi 1. Okay, so if you simplify this, what will be the values? Okay, so let me use this part of the board. So for the first integral between 0 to TB, let me write it down. So phi 2 dash is basically S2 divided by v root TB minus, the first integral is 1 over TB. So this v square cancels, so 1 over TB, and this will be TB by 2, so it will be half. So minus phi 1 by 2, and the second integral is again this v square cancels, so this is minus 1 over TB, and this is actually minus half, and then minus half become plus half because we have another minus sign here. So this is basically plus phi 1 by 2. So these two terms cancels. So we have basically phi 2 dash as S2 divided by v root TB, and we can get phi 2 by normalizing phi 2 dash like this. So what will be the norm of phi 2 dash? The norm of phi 2 dash will be the integral of this quantity, integral of the square of this quantity, integrated over all values of dt. So if you see that in the numerator you will have S2 square, in the denominator you have v square TB, and S2 square integrated over all values of t will give you the energy of S2, which is v square TB. So v square TB and v square TB will cancel out, and the norm of phi 2 dash is basically 1. So phi 2 is just equal to phi 2 dash, and that is basically S2 divided by v root TB. So you have calculated your phi 1 here, that is equal to S1 divided by v root TB, and your phi 2 is calculated here, which is your S2 times v root TB. So now if you look into this diagram, so basically if you say that your v root TB, or let's say your v square TB, is the energy of the signal. So both signals have equal energy, v square TB. So v root TB is square root of E, and you can see that your your phi 1 was basically S1 by square root of E, as you saw in the calculations before, and your phi 2 is basically S2 divided by square root of E. So therefore you can write this, like write S1 and S2 as as linear combinations of phi 1 and phi 2. So S1 is basically square root of E times phi 1 plus 0 times phi 2, and your S2 is basically 0 times phi 1 plus square root of E times phi 2. So if you see, it's also a two-dimensional signal space. If you work out through Gram-Schmidt and try to find out phi 3, you will find it as 0. So phi 1 and phi 2 are enough for representing these two signals, S1 and S2, and your your S1 is along the phi 1 axis and it has a 0 component along phi 2 axis. So your S1 is here and the amplitude of your S1 is square root of E. So this is the amplitude of your S1, and again your S2 is along the phi 2 axis and it has a 0 component along phi 1 axis. So your S2 completely lies in the phi 2 axis and its amplitude is again square root of E. Okay, so these are the two signals denoted by this signal space defined by phi 1 and phi 2, and your phi 1 and phi 2 themselves look like this. So phi 1 is S1 divided by square root of E. So basically the shape of phi 1 is same as S1, only the amplitude is changed or scaled down, and similarly the shape of phi 2 also looks same as S2 because your phi 2 is S2 divided by square root of E. So the amplitude is scaled down. So in this way, given any set of signals, you can calculate the orthonormal basis functions using Gram-Schmidt procedures. So I would encourage you to work through more examples that are there in the book that I'm following, Digital Communication by Ha and Gwen, and you can understand it more strongly. And later on, I will also try to solve some more problems, and you will be able to appreciate it further through those solved examples. So I will stop here today, and we'll see you in the next video lecture. Thank you.